Okay, so let us start today's session. Uh, Hello and welcome to this NPTL TA session for heat transfer course. And today we will be discussing problems and some concepts related to week 4 course content. So, this is basically week 4 course content. And in week 4, if you remember, we the most we started something a different mode of heat transfer, that is convection. So we'll solve problems, but before that we can just do a quick recap of some important concepts, and then we can start solving problems. So if you remember, this convection, it uses motion of fluid for heat transfer, and this heat transfer, because of motion of fluid, is actually very complex in nature. But if you see the simple relation that we have, that is from the Newton's law of cooling, which is a very simple expression, which states that Q is equal to HA times of delta T. So all the complexity that is related to this heat transfer is captured into one single parameter, that is the heat transfer coefficient. So this heat transfer coefficient is a very complex term and depends upon many factors, like, let's say, density, viscosity, specific heat, thermal conductivity, and many more. But all these complexities that we have here is captured into this single parameter. This is why we could able to deal with problems related to convection with simplicity. Now, how do we obtain, or how do we relate this heat transfer coefficient with other parameters? Like, how do we estimate these values of heat transfer coefficient? So, if you remember from the lectures, you studied about some dimensionless numbers. Okay. And we will be discussing about, I think, in heat transfer, we have two major dimensionless numbers and one related to flow, that is the Reynolds number that we already know. So the first dimensionless number is the Nusselt number, which is nothing but h times of some characteristic dimension by k. Then we have Prandtl number, which is nothing but Cp mu by k. And then we have our, what we already have, that is the Reynolds number, rho v d by mu. Now, if you see, let us try to first understand what are the significance of these dimensionless numbers. So let us start with this Nusselt number. If you see this Nusselt number, if you write something like this, let's say I'm writing this is the characteristic length divided by k times of a, whole divided by I'm writing 1 by h times of a. So I have multiplied both numerator and denominator by a and written it something like this. So if you see this term, what we have here is nothing but the conductive resistance of the fluid. And this term here is nothing but the convective resistance of the fluid. So this term, this Nusselt number, this actually gives you an idea of the dominance of a particular mode of heat transfer. Okay. Say for example, if you have Nusselt number is equal to 0. Okay. Then what will it signify? So if Nusselt number is equal to 0, that means there is no conductive resistance. You see, this is nothing but conductive resistance by convective resistance. So if Nusselt number is equal to 0, that means the resistance due to conduction is not present. This means the heat transfer is purely by conduction. So you see, from this value of Nusselt number, we can get an estimate of which is the dominating mode of heat transfer in a particular system, or relative importance of the, we can see here we have convective resistance and conductive resistance. So we can say that Nusselt number measures the relative importance of convection and conduction. Okay. Similarly, next we can see Prandtl number. Okay. So this is Cp mu by K. So we can write it something like this: mu by rho divided by, we have K by rho Cp. So if you see this term, what we have is the momentum diffusivity. And this is, we already studied this. This is nothing but the thermal diffusivity. So just like previous, here the Prandtl number signifies the relative importance of thermal diffusivity and momentum diffusivity. Someone has asked one question, sir, is Nusselt number and Biot number the same? No. See, The major difference that we have is here the thermal conductivity that we use is the thermal conductivity of the fluid. Okay. In Biot number that we use is the thermal conductivity of the solid that we use. Okay. Okay. So I think this is clear. What is Nusselt number? What is Prandtl number? Now, let us try to solve one problem. Okay. No, before that, okay. Before that, let me tell you one more thing. This Nusselt number that we have. Okay. So you have seen in the lectures that how to solve problems related to Nusselt number, and that means how to relate conduction with convection. So we'll do one similar problem. Okay. Okay, so let us try to do one question. Let me write the question. Say the temperature distribution okay, inside a thermal boundary layer. Okay, inside a thermal boundary layer over a heated isothermal flat plate. Okay, over heated isothermal flat plate is given by T minus EW divided by T infinity minus TW, which is equal to T by 2 Y by delta T minus 1 by 2 Y by delta T cube. So calculate the local Nusselt number. Okay, based on this thermal boundary layer thickness. So you can try this question and then we can see how to solve this. Okay, let me draw. I think it will be easier so you can understand it. Like this. So here we have T infinity, and this is the plate, and this is TW. And this is obviously y is equal to 0. And then this is the thickness, this delta T is the thickness of this boundary layer. Okay. So you can try this question. So let us try to see how to solve this question. So we have to calculate the local Nusselt number based on thermal boundary layer thickness. Okay. So the first thing you have to understand is that here uh, to calculate the Nusselt number, we know we have to obtain a balance between the convective heat transfer and conductive heat transfer. Because if you remember, it is the ratio of conductive heat transfer resistance due to conductive heat transfer to that of the resistance due to convective heat transfer. So the heat that is lost due to convection is nothing but the heat that is coming by conduction. So let me write that here. So convective heat transfer will be equal to will be same as the conductive heat transfer. Now, what will be the convective heat transfer? You see, you have two different temperatures, that is Tw minus T infinity. So, this is the heat that is lost due to convective, uh, heat, like convective transfer of heat. So, we can write, let's say there is some heat transfer coefficient. So, we can write it as H A Tw minus T infinity, and that is same as the conductive mode of heat transfer, that is nothing but minus K A, we have dt by dy, and at y is equal to 0, that is at this point. Now from this temperature profile we can actually obtain this variation of temperature or the temperature gradient along the y direction. So if we calculate dt by dy, that is nothing but, you see, will be T infinity minus Tw. Here we have 3 by 2 times of delta T minus 3 by 2 y minus delta T square times of 1 by delta T. And this is evaluated at y is equal to 0, because we want dt by dy dt by dy at y is equal to 0. So this is also evaluated at y is equal to 0. So if we substitute y is equal to 0, this entire term will go to 0. So this will be nothing but T infinity minus Tw times of 3 by 2 times of delta t. So if we substitute this back here, we get A and A will be cancelled out. This A and A will be cancelled out. So we have H times of TW minus T infinity. This is equal to minus K times of T infinity minus TW 3 by 2 times of delta T. So you see this and this will be cancelled out with this minus sign. So what we are left out with is H delta T divided by K. This is equal to 3 by 2. This implies what is this? This is nothing but the Nusselt number based on the thermal boundary layer thickness. So you see Nusselt number based on the thermal boundary layer thickness. So we have Nusselt number will be equal to 3 by 2 or 1.5. No, we TW. See, I have taken the differential, right? So when we take the differential, that TW will go out. It is a constant term. Okay, because I have directly written the expression for dt by dy. So if you take dt by dy, term will go. This term will go out. Okay. Okay. So let us try to see some more problems. So choose the incorrect statement from the given options. So you can give it a read and then you can try to give the answer and then we can discuss. Okay, so let us see. So choose the incorrect statement from the given options. If fluid in direct contact with a solid sticks to the surface due to viscous effects and there is no slip, this is known as the no slip condition. So this is correct, right? Because when we have a solid and the fluid in contact with the solid, we call it the no slip boundary condition. The layer that sticks to the surface slows down the adjacent fluid layer, which slows the next layer, and so on. Therefore, the no slip condition is responsible for the development of the velocity profile. So that is also correct. So you know, so here the velocity will be zero. This will slow down the this layer. So this will have some decrease in some velocity, and similarly some velocity till it goes to 99% of the velocity. And this is why we get this kind of profile. So this is also correct. The flow region adjacent to the wall in which the viscous effects are not significant is called the boundary layer. So this is obviously not correct because the viscous effects are very significant in the boundary layer. An implication of the no slip condition is that heat transfer from the solid surface to the fluid layer adjacent to the surface is by pure conduction since the fluid layer is motionless. So this is also correct. So the incorrect statement is this one. Okay, let's move on to the next question. So again, you can try this. So let us discuss this question. For a given value of Nusselt number, convective heat transfer coefficient is, choose the incorrect option, is inversely proportional to the characteristic length of the system and does not depend on the thermal conductivity. Okay. So if you see the value of, for a given value of Nusselt number, the convective heat transfer coefficient, this H value, it does not depend on the thermal conductivity, correct? But it is inversely proportional to the characteristic length. So this is obviously correct. We have inversely proportional to the thermal conductivity and inversely proportional to the characteristic. Inversely proportional to the thermal conductivity and inversely proportional to the characteristic length of the system. So you see, I think this is choose the correct option, right? I think it is, because if you see, we have Nusselt number. This is equal to H LC by K. So for a given value of Nusselt number, so this is known. You see, this H is equal to K by LC times of Nusselt number. So H is directly proportional to the thermal conductivity and H is inversely proportional to the characteristic length. Okay. So I think this is the, you have to mark the correct option, not the incorrect option, because it is inversely proportional to the characteristic length, that is correct, and does not depend on the thermal conductivity. So this is not correct. Inversely proportional to the thermal conductivity, no, and inversely proportional, this is also not correct. Directly proportional to the thermal conductivity and inversely proportional to the characteristic length, this is correct. Okay. And directly proportional to thermal conductivity does not depend on the characteristic, this is also not correct. Okay. So this is the only correct option. Okay. Now try this question and then we will discuss. Okay. So let us discuss the temperature of a gas stream is to be measured by a thermocouple whose junctions can be approximated as a 1 diameter sphere. So we can see there is a gas stream and uh, whose temperature is to be measured by a thermocouple whose diameter is 1 The properties of the junctions are given. So this junction, the properties are given. Thermal conductivity is given. Density is given. Cp value is given. And the convective heat transfer coefficient between the junction and the gas is this much. Determine how long it will take for the thermocouple to read 99% of the initial temperature difference. So these are some of the assumptions. That is, the junction is spherical in diameter, and we have thermal properties of the junction, such as heat transfer coefficients and other things are constant, and there are negligible radiation effect. And the characteristic length of the junction can be assumed to be the ratio of the volume to the surface area of the sphere. Okay. So let us try to solve this question. So here it is given that the characteristic length of the junction can be assumed to be the ratio of the volume to the surface area of the sphere. So we can directly calculate the characteristic length, that is the V by A. So if you see, this is a spherical junction. So the volume we can write 4 by 3 pi r cube divided by 4 pi r square. So that is nothing but r by 3, or we can write it as d by 6, which is nothing but d is 1 So we can write 0.001 divided by 6. Okay, which is 1.67 times of 10 to the power minus 4 meters. So one thing you can see here is this is like a lump mass system. That means we can assume that the temperature of this thing increases uniformly. Okay, so there are negligible uh, heat transfer due to conduction within the solid junction. And how do we know that? We can calculate the Biot number for that. So let us calculate the Biot number. that is H LC by K. So this heat transfer coefficient is 210 and this LC is 1.67 times of 10 to the power of minus 4 divided by thermal conductivity of the solid. So if you substitute all the values, you will get 0.001. And if you remember, the value of Biot number has a limit of zero point 0.1. If it is less than 1, then we can assume the system to be a lump mass model. So you can see this is clearly less than zero point 0.1. So the lumped mass, let me write lumped mass analysis can be applied here. Okay. So let me erase this. Okay. Now, if you remember, how was the temperature distribution for such a case? We can write T minus T infinity by Ti minus T infinity. This is equal to we have some terms of exponential term, right? We have here we have some constant property constants and dependence on time. Where this property constant, if you remember, that is nothing but HA by rho V Cp. This V by A, again we can write this as the characteristic dimension, that is rho LC times of Cp. So this is nothing but 210, this 210 divided by the density, which is nothing but 8500. Characteristic dimension is 1.67, 10 to the power minus 4 that we derived. And then we have Cp value, which is nothing but 320. So if you calculate this, you can get 0.462, and this is second inverse. Okay, so B we already know. Now we have to calculate the time, determine how long in seconds will it take for the thermocouple to read 99% of the initial temperature. Okay. So we have to obtain what is the time it will take to read this 99% of the initial temperature. Now we know, we since we don't know the initial temperature, we don't even want to know the uh, like we don't need to know the initial temperature for this situation, because you see 99% of the initial temperature difference. So if initially we have a temperature difference, we have Ti minus T infinity is the initial temperature difference, then we have to reach the 99% of this initial temperature difference. Okay. So to reach the, like, in order to reach this 99% of the initial temperature difference, for that we need to have this T minus T infinity should be equal to nothing but if this is 99%, then what is the temperature that is left? That is 1 minus 0.99. So if you substitute this here, you can get, sorry, this is nothing but 1.99 times of Ti minus T infinity. So if you substitute it here, what we can get is 1 minus 0.99 is equal to exponential of minus times of B times of T, where B you already know to be 0.462. Okay. So if you substitute the value of B, you can get the value of time to be equal to 10 seconds. So the correct answer is 10 seconds. Okay. So now let's move on to the next question. So this is again a very simple question that we have already done similar question previously. So you can try this again, then we can discuss. So this question, I think we have already done similar question previously. So walls of a cubical oven of thickness L, they are made of material of thermal conductivity K. Temperature inside is 100 degrees Celsius, and the heat transfer coefficient is 3K by L. If the wall temperature on the outside is 25, what is the inside wall temperature in degree? Okay. So we know that the outside is 25. So we can write the total heat, that is 100 minus this is the temperature difference between inside and outside, divided by sum of all resistance that we have, which is nothing but it has a wall of cubical oven of thickness L, and which is made up of thermal conductivity K. So that is for one resistance that we have. So that is L by K, plus we have an inside heat transfer coefficient of 3K by L. So we have uh, so the resistance will be L by 3K. So this is same as that of, if we equate it with, let's say, from, so it is something like this, right? So this is a wall. We have some convection resistance and then conduction, and then we have 25 degrees Celsius. Here we have 100 degrees Celsius. So here we have convective heat transfer coefficient H, which is nothing but uh, which is nothing but 3K by L. So we have to find the temperature here. And for this we have L by K as the net resistance. So to find the temperature here, between this and this, we have to add total resistance. Between this and this, we have to incorporate only this resistance, that is 100 minus T divided by L by 3K. So if you simplify this, you will get temperature to be equal to 81.25 degrees Celsius. So again, you can try this question. This is also very straightforward. Okay, so choose the correct option. The buoyancy forces is the primary driving force in free convection. So this is correct. Free and forced convection can never occur simultaneously. So this is not correct. There are situations where the contributions of both free and forced convection are taken into account simultaneously, but the direction is always opposite with respect to each other. This is also not correct. Both A and C are correct. So since C is not correct, so obviously yes, option A is correct. So let's move on to the next question. So you can look at the question and give it a try, and then we can try to solve this. This type of question also, I think we have already done. So you can try and then we can solve. So we can try to solve this question. Okay. So it is given during the flow of air at T infinity to be 20 degree Celsius over a flat surface maintained at a constant temperature of 160 degree Celsius. The dimensionless temperature profile within the air layer over the plate is determined by this expression, where A is this particular constant and Y is the vertical distance measured from the plate surface. So this is the Y direction. Consider the radiation heat transfer to be neglected and given the K value to be this. So determine the heat flux on the plate surface. So the heat flux from the solid surface to the fluid layer that we will be calculating can be determined by, very, we know the direct relation, that is Q is equal to minus K times of dou T by dou Y, or since this is only a function of Y, we can write direct differential of this dt by dy, that is at Y is equal to 0. So dt by dy we can calculate from the temperature distribution that we already have. So we will be having Ts minus T infinity times of this, we have e to the power minus ay. So we have minus a times of again e to the power of minus ay. And this to be evaluated at y is equal to 0. So we have y is equal to 0. So this is nothing but Ts minus T infinity times of minus A. So we already know Ts to be 160. So this is nothing but 160 minus 20 times of minus A, which is 3200. We have minus 3200. And we substitute it here to get Q is equal to this minus, and this minus will be plus. So we have 0.03024. 0.03024 times of this is 140, and we have 3200. So if we calculate it, we will be getting 1.35 times of 10 to the power 4 watt per meter square. So this is the correct option. Now let's see the second part, that is obtain the value of convective heat transfer coefficient. So now how we can obtain the convective heat transfer coefficient? We can equate conductive heat transfer to the convective heat transfer. That means we can write H times of Ts minus T infinity will be equal to minus K times of dt by dy at y is equal to 0. And this value, this we already obtained this to be how much? You see, this is nothing but minus K, and this dt by dy at y is equal to 0 is this Ts minus T infinity times of minus A. So this Ts minus T infinity will be cancelled out. This implies what we have, H is equal to nothing but K times of A. Okay. So this is nothing but we have 0.03024 times of 3200, which is nothing but 96.8 watt per meter square Kelvin. So this is the correct option. Okay, so now we have four true false questions that we can try and then we can end today's session. Okay. So the first is the Prandtl number of any particular fluid generally varies with temperature. Is this true or false? So if you see the Prandtl number, that is nothing but Cp times of mu by K. So you know Cp is actually a function of temperature. Viscosity is also a function of temperature. Okay. So all these are, you see, functions of temperature. So this Prandtl number is also a function of temperature. So this is true. K is also function of temperature. Let's see next question. In the expression of Nusselt number, K indicates the thermal conductivity of the solid. Is it true or false? Yes, that is correct. That in Nusselt number, as we discussed, HLC by K, this is the thermal conductivity of the fluid. But in Biot number, we use HLC by thermal conductivity of the solid. So this is false. While performing a shell balance to a system consisting of a fluid with low viscosity and high velocity gradient, we can neglect the effect of viscous dissipation. This is true or false? So if you remember that the viscous dissipation term has some relation, something like dou v z by some, let's say I'm writing it in generalized form, dv by dn, and we have a square dependency. Okay. So you see, we have a high velocity gradient and this has a square dependency. So the effect of viscous dissipation here, we cannot be neglected. Okay, so it is false. The value of Prandtl number is always less than 1 as thermal boundary layer grows faster than the momentum boundary layer. Is this true or false? True. Okay. So this will actually be false. Okay. Why? Because if you see what is the definition of this Prandtl number, you know, Prandtl number nothing but Cp mu by k. And if we rearrange it and write as we have discussed here, this is momentum diffusivity by thermal diffusivity, right? So let me write, this is momentum diffusivity divided by thermal diffusivity. Okay. So here three situations are possible. One, when Prandtl number is equal to 1, when Prandtl number will be greater than 1, and when Prandtl number will be less than 1. So you see, when we have Prandtl number equal to 1, that means both momentum diffusivity and thermal diffusivity are same. That means both the boundary layers, if you see what do you mean by diffusivity, let's say we have a flat plate, something like this, and the boundary layer is developing, right? And say boundary layer is diffusing into the fluid. So here the boundary layer is diffusing into the fluid. Since both the diffusivity terms are same, the they both the boundary layers will overlap. That means they will be same. Okay. But what will happen in the what will happen in other cases? say when Prandtl number is greater than 1. So in such a case, what will happen? Let's say we have a surface, and obviously both of them will start to diffuse. But you see, the Prandtl number is greater than 1. Which means the diffusivity, the how do I say? The diffusivity that we have, let's say uh, this momentum diffusivity will be greater than the thermal diffusivity. Correct. That means what? Let's say the fluid is coming from this direction, then this momentum will be easily diffused. Okay. Since it is easily diffused, it will reach the maximum layer very quickly. Okay. So therefore, this boundary layer thickness will be smaller. Okay. Because you see here we have this, in this case, the momentum diffusivity will be greater than the thermal diffusivity. So this momentum will diffuse, the diffusivity of this momentum is much easier. So when do we see this boundary layer? You see, when we have restrictions, more and more restrictions, it will be more wider and wider. It will go more up and up. Since the diffusivity is larger, that means it will easily diffuse, and therefore the momentum layer that we will be having will be lesser than the thermal boundary layer. Okay. So this, let's say, is the delta, we can say, uh, sorry, what I say. So you see, this momentum boundary layer will diffuse, and therefore we will be having this as the momentum boundary layer, and this we will be having a smaller thermal boundary layer. Correct? So let's say, let me write it as delta T, and here we have delta. Similarly, we can say, let's consider the last part where Prandtl number is less than 1. So again, if you see, for this case, we will be having, again, we will be having thermal boundary layer, thermal diffusivity. This will be higher than the momentum diffusivity. So if we have a surface, something like this, since we have higher thermal diffusivity, we will be having a higher diffusion into the fluid. And let's say this is delta T. And similarly, since we have less momentum diffusivity, this will be less. This is delta. Okay. So you see, the value of Prandtl number is not always less than 1, because thermal diffusivity can be greater than momentum diffusivity, or momentum diffusivity can be greater than thermal diffusivity. Okay. So this is the last question for today's session. I hope you enjoyed the session, and we will again meet next week, same time, with more questions from the next week's course content. So till then, you practice more questions, and then we can discuss some more problems. I can give you an example like where you can see this in practical situations, like this Prandtl number less than 1. You can generally see this in, let's say, kind of liquid metals. In practical, if you see, liquid metals show this kind of behavior. Like example, mercury is the example of liquid metal. And similarly, Prandtl number greater than 1. Generally, all kind of liquids that we have show this behavior. And Prandtl number equal to 1 is generally shown by all gases. So you can get an idea of which kind of behavior is actually shown by what kind of fluids. Okay, so this is it for today's session. So I'll upload this file and you can access this. So thank you. Yes, it is written that it is always less than 1, but it is not always less than 1. Okay, it is given value of Prandtl number is always less than 1 as thermal boundary layer grows faster than momentum. It is not always true. Okay. Okay, thank you and bye. And we'll again meet next week. Okay.